It won't be visible to me, right? So anyhow, did you log the meeting at least?
No.
Huh?
No,
Yeah,
nobody will enter.
Nobody will enter now. Yeah, that is better. Okay, I hope yesterday you had some like a better kind of approach for your revision. Okay, and these sessions for that only, so that you, like, if at all in the last minute, if at all you are having still some kind of confusion for any particular topic, you will be able to overcome that. Okay, now today we are going to kind of brush up the concepts when it comes to the quantitative analysis of the organic compounds. Now here the thing is, let us see the few questions here. Okay, now in this particular question, see, the thing is, they are asking you, sometimes they may ask you to identify what is the percentage of carbon, what is the percentage of hydrogen, what is the percentage of nitrogen, or any halogen, or any like sulfur or something like that, right? Now the thing is, how do we go for it? Okay, now the thing is, you must remember, you just need to remember one thing, that what is the form in which that particular element is getting converted into, right? If you just remember that, you just have to apply the mole analysis after that, right? So the thing is, when it comes to carbon and hydrogen, we are doing certain kind of, that Lebig's experiment is there, and based on that, that carbon is getting converted into CO2 and hydrogen is getting converted into H2O, right? Now the thing is, you just need to understand the language of the problem here. Okay, so here they have given you on the complete combustion, this much of the organic compound gave 0.198 gram of carbon dioxide and this much amount of water. Okay, so all you need to do apply here is, you must remember only two things, or else just remember in which form this carbon is getting converted when you are carrying out the experiment. It got converted into CO2, right? So I'm saying that carbon is getting converted to CO2, hydrogen is getting converted to H2O. Now you try to see, simply if at all I say 1 mole of CO2, it contains how many moles of carbon? It should contain basically 1 mole of carbon, right? So 1 mole, you just apply the mole analysis, 1 mole of CO2, it contains 1 mole of carbon, right? That is, if I want to write down, this is 1 mole of this means 44 gram, and this is giving you 12 gram of carbon, right? This much you can do easily. Now in the question, they have mentioned something that 0.198 gram of carbon dioxide is formed. So can you find out 0.198 gram of carbon dioxide, it corresponds to how many grams of carbon? So this will be 12 into 0.198 upon 44. So this is the mass of carbon which you got. Now they are asking you, or the examiner will be asking you the percentage of carbon, right? So the percentage of carbon will always be given by mass of the carbon upon mass of the organic compound into 100, right? So all you need to do is take this value, divide by whatever is the mass given to you, 0.246 into 100, you'll get the answer. It's very simple. Now the similar thing you have to apply even for your hydrogen also. So in case of hydrogen, what I'm going to write is 1 mole of H2O, it gives me 2 moles of hydrogen, right? And you need not remember any formula here. You just have to understand this thing, okay, basic. So now here, this means what? 18 grams of water. It is giving you how many? 2 grams of hydrogen. So how many you are having now? Therefore, 0.1014 gram of water. It will give you how much amount of hydrogen? So that will be 2 into 0.1014 upon, basically it is 18. So this is, you have got as mass of hydrogen, right? And once you get the mass of hydrogen, all you need to do is divide this mass of hydrogen with the mass of organic compound into 100 to get the percentage of hydrogen. So you need not mug up any kind of, formula here, right? Clear about this? I hope everybody is clear about that. Now, when it comes to Dumas method, okay, in Dumas method, what we are doing is basically the organic compound we are taking, okay, and that organic compound is basically being, kind of sent to this furnace where the nitrogen in it is trying to get converted into N2. So we are kind of trying to estimate the amount of nitrogen or the percentage of nitrogen in the form of N2 gas, right? Now the thing is, here there are certain kind of copper oxide, these gauges are there. So the thing is, some of the nitrogen may get converted into oxides also, okay, nitrogen oxides. Now the thing is, we just want nitrogen from here. So that is the reason there is a copper gauge in the end which will be acting as a reducing agent. which will reduce any oxide of the nitrogen which is formed back to the nitrogen. Okay, so ultimately what we are going to do is we are going to collect nitrogen above this particular system which is here. Okay, so here you are having basically sodium hydroxide solution. Over that you are basically collecting your nitrogen. So if at all there is any CO2 H2 which is there, CO2 will be absorbed in this. Okay, so ultimately I need to collect using N2. Okay, now next what we are going to see is the calculation part of it. Okay, now in the calculation part you just try to understand certain things here. So in the calculation part, all you need to understand is we have got N2, right? But this N2 is moist N2, right? Because the nitrogen gas which is liberated, it will be hot and it will be carrying along with it the water vapor with it. Okay, so ultimately whatever the pressure we are recording, that is of pressure of moist N2, and that will be equal to pressure of dry N2 plus the vapor pressure of water at that particular temperature, vapor pressure, or else we call this as aqueous tension, right? This thing will be given to you in the data. This will be also given to you in the question, right? Okay, now, so I'll directly take up the question now. So you have got the basics of it. Okay, now the ultimate thing what you have to do is you have got the pressure of dry nitrogen. Okay, but the experiment which you are performing, this is not at STP condition. Okay, so what you're doing, what you have to do is we want to use one particular statement that 1 mole of nitrogen at STP, 1 mole of nitrogen gas at STP, it is going to occupy 22.4 liters. So I want to use that particular statement, right? So the thing is, I want what volume of the nitrogen. This is not at STP, this is at non-STP condition. So I want to convert this into STP conditions, and then I'll relate it. Okay, so let us see using one question itself, right? Need not worry about any kind of formula here. You just look at the question. What is given to you is in Dumas method for estimation of nitrogen, 0.3 gram of an organic compound gave 50 ml of nitrogen, right? So you are knowing what is the mass of organic compound which you have taken, that is 0.3 gram. Okay, and it gave 50 ml of the nitrogen. So the volume which you collected at 300 Kelvin, that means it is not at STP, no, right? So we have got the volume of nitrogen. How much? It is 50 ml, right? At 300 Kelvin. Now next is at 715 mm pressure. And again, this pressure will be of whom? That will be of the moist one. Okay, and calculate the percentage of nitrogen in the compound, and they've given you aqueous tension also. So first thing what you're going to do is, you know the value of nitrogen which you have collected. Let us say this is 50 ml. Now the pressure of dry nitrogen I'm saying here, that will be basically 715 minus 15. Are you able to understand why I've done 715 minus 15? Right? Because it is like moist nitrogen, pressure of the moist nitrogen equal to pressure of dry nitrogen plus the aqueous tension, and that is the reason we have got this as 700, right? Now this is 700 mm of Hg, and this is not at STP condition, and we also know the temperature also. Temperature is 300 Kelvin. Now you have already studied in the gaseous state, no, that P1 V1 by T1 equal to P2 V2 by T2. Now I'm saying that we want to find out, this is the volume of nitrogen collected at non-STP condition. So what is the volume of nitrogen will be collected at the STP condition? Matlab, how much it will correspond to, like how much of the volume of this particular nitrogen will correspond at STP condition? Equivalent we are trying to find out. Okay. Now the thing is this, all this or else entire this thing corresponds to the STP condition. So in STP, it's only the temperature and pressure is known to us, right? So here what you are going to do is you are going to put 700, you are going to put volume as 50, you are going to put this as 300. You want to find out the volume of nitrogen at STP. Pressure will be 1 atmosphere, means 760 mm of Hg. This is 0 degrees Celsius, 273. So you will end up with the volume of nitrogen which they have collected here. Let us say it is 41.9 ml. Okay. Now after that, what you need to apply is, basically you know that 1 mole of nitrogen at STP, it occupies how much volume? 22.4 liters, or else you can say that 22,400 ml. And what is the mass of 1 mole of N2? Mass of 1 mole of N2 is 28 gram, right? So 28 gram of N2 corresponds to 22,400 ml. So what you are now having is 41.9 ml will correspond to what mass of nitrogen. So you'll be getting easily 28 upon 22,400 into 1.9. So you got the mass of nitrogen. Now you need to find out the percentage. So for percentage, what you do? For percentage of nitrogen, all I need to do is mass of nitrogen upon the mass of organic compound into 100. That's what we do. So it is as simple as that. Okay. So I hope it is clear to all of you. So here also there is no need to remember the formula. Now next is Geldahl's method. Basically, Geldahl's method is important also, right? Now when it comes to Geldahl's method, you just remember like these, like only for the estimation of nitrogen, things are a little bit different, okay? Otherwise, all you need to remember is in which form it is getting converted, a particular element, okay? Now here, if you see, what is done here is, in the Geldahl's flask, first of all, we take the organic compound and we add the concentrated H2SO4 there. And CuSO4 acts as a catalyst, right? So what does this concentrated H2SO4 does? That whatever is the nitrogen present in the organic compound, it converts it directly to the ammonium sulfate, right? So what I'm having is this organic compound, right? This organic compound, or in fact, I'll do one thing. I can just go for this. And we'll come back to this particular question. So I'm just explaining you here Geldahl's method, because it is the area which is like confusing for everybody. Okay. Now in this case, what we do is, in Geldahl's method, basically, first of all, I told you that in the Geldahl's flask, which you are able to see, in that Geldahl's flask, basically what we take is, we basically take your organic compound which contains nitrogen, because the thing is, we have already, kind of detected which particular element could be there. Okay. So what we do is, the first step is, we take that organic compound, having nitrogen. In that, we add the concentrated H2SO4, right? And then what will be happening is, all the nitrogen will get converted to the ammonium sulfate. That's what we have seen, right? That's what the first step which happens in that flask. Okay. Now from the Geldahl's flask, it will be like, kind of shifted to another, equipment. In that, what is done is, this ammonium sulfate which is there, it is reacted with NaOH. And here we are trying to, kind of liberate nitrogen in the form of ammonia, right? So here you are going to get ammonia plus Na2SO4 plus H2O. That's what we do, right? Because the thing is, you can easily write this as NH4 plus and SO4 minus 2. And this is like Na plus and OH minus. So this can further be written as ammonia plus H plus, right? So you are having this H plus and OH minus as water, Na2SO4 and ammonia, right? So ammonia, nitrogen got liberated in the form of ammonia, right? Now the thing is, if I leave this ammonia like that, it will be like lost to the atmosphere. And ultimately, I have to estimate my nitrogen only in the form of this ammonia. So I need to make arrangements so that we can capture this ammonia. Okay. So how do we do that? You'll see that there is a kind of, there is a like equipment where it is written Geldahl's trap. Okay. So in Geldahl's trap, we are basically taking this ammonia. We are adding excess of this H2SO4. Excess, but this will be known amount. Because you will be doing all those stoichiometry on the paper and you will be like approximately able to understand that, or else this much should be required. So based on that approximation, you are able to add. Okay. Now the thing is, what will happen here is, you'll be having ammonium sulfate form. We have captured it, right? Now the thing is, when I have taken this in excess, some amount of H2SO4 will be definitely left out, right? So I'm just writing here this H2SO4 left out. Yes or no? This is only for understanding purpose. This you will not involve in the balancing. Okay. Now, next what happens is, we want to find out, if at all we are able to find out how much amount of H2SO4 is left out, then I'll be able to find out how much of H2SO4 reacted. Okay. So what we are going to do is, we are going to again titrate it. So this is like H2SO4 left out plus the NaOH, so that I'll be getting Na2SO4 plus H2O, right? Now the thing is, its amount can be known to us. In fact, this one will be like its molarity and its volume, it will be known to me, right? So are you able to understand what is all happening in this entire, setup? You are having in this particular flask, you might be doing some kind of, the first reaction where you are decomposing it. So the first reaction is related to the decomposition of the organic compound which contained nitrogen. So it is getting converted into ammonium sulfate, right? Now you're trying to do is, what you're trying to do is you shifted it to another flask in the another setup where you have added NaOH so that ammonia could be liberated from there. But if you make this or let this ammonia go free, you will not be able to estimate nitrogen in that form. Right? So what we are trying to do is we are now trying to capture that ammonia. How? By basically treating it with excess amount of H2SO4 so that or whatever the ammonia is trying to escape, it gets converted into ammonium sulfate. And definitely when I'm taking this in excess, this is the known amount. I know what will be the normality of it, what will be the molarity of it. So I know what is the H2SO4 like. There will be definitely some amount of H2SO4 left out. So I want to find out what is this H2SO4 which is left out. Right? So in fact, you can see like this in this beaker, you'll be having something like this. In this, you are having basically ammonium sulfate is there, right? And now the thing is what you have done is basically there is some H2SO4 left out also in the last beaker which is there. Whatever, the thing is you have added H2SO4, now it has kind of, reacted with entire ammonia and it has formed ammonium sulfate. Now whatever is the H2SO4 left out, it is like this only. So what we are trying to do is, we'll be doing the titration now. So if at all I want to show this diagram, it will be like something like this titration. Okay. And in this we are taking known volume, or else normality or its molarity will be known to us, and we'll be adding some indicator, right? Like methyl orange, and it will be able to show the color change, and we'll be able to see like when to stop this particular reaction. Okay. So you must know all these things first of all. So basically the equation which is for use for us is this, only these last two equations. Okay. Now, either we can do it by the equivalent method or else we can go by the normal mole-mole analysis. Only difference is if you're going by the mole-mole analysis, you make sure that you are balancing the equation. And if you are not going by mole-mole analysis, in that way, you just have to, kind of apply, like you need not balance, you have to apply the equivalent concept. Okay. Now the thing is here, its normality will be known to me, right? Let us say this, for this it is N1 V1 and this is for N2 V2 is there, right? Now the thing is, can I write for this equation number of equivalents of H2SO4 left out? That will be equal to number of equivalents of NaOH, right? And we know that the normality is equal to what? Number of equivalents upon volume, right? So basically it will become N2 into V2. So I came to know about how much amount of H2SO4 was left out. Okay. Now, next what we need to do is, do I know that the number of equivalents of basically H2SO4 taken in excess? Do I know about that? Yes, I know that, which is N1 into V1. Are you able to follow everybody? Because I'm just again brushing this particular technique because as such I've already taught you in detail. Only thing is these things students tend to forget. Okay, that is the reason I'm just revising it. Now, if at all, I basically subtract this. This is 1 and this is 2. If at all I do like this, 1 minus 2, will I be able to get the number of equivalents of H2SO4 reacted? Right? That will be equal to N1 V1 minus N2 V2. Will I be able to get that? Yes, because I know how much excess I have taken and how much actually it is left out. So the difference of 2 will give me how much of the H2SO4 reacted. Okay, now if I know how much of the H2SO4 reacted, so the H2SO4 reacted with whom? In the third reaction, your H2SO4 reacted with whom? It reacted with ammonia, na? Right? So do I get this as equal to the number of equivalents of ammonia itself? Right? Yes, correct. Now the thing is, can I write this number of equivalents of ammonia same as number of moles of ammonia? Because N factor for ammonia is 1. Why? Because when you put ammonia in water, what you are going to get is NH4OH. And it is going to just supply, as such it is a weak base, but still it will be able to give you 1 OH minus, right? So that is the reason I have directly written that the number of equivalents of ammonia is same as number of moles of ammonia. Now you have come to a number of moles itself, right? So one number of moles of ammonia will be equal to the number of moles of nitrogen or not? Because 1 mole of ammonia contains 1 mole of nitrogen. So if I give you 2 moles of ammonia, it should contain 2 moles of nitrogen, right? Now from number of moles of nitrogen, can I find out what is the mass of nitrogen? That is number of moles of nitrogen into molar mass of nitrogen. So whatever it is, it will be like into 14 you do. This much is the mass. Now can you calculate the percentage of it? So percentage of nitrogen will be mass of nitrogen upon the mass of organic compound into 100. Right? So just keep one thing in mind, that whenever a kind of question from based on Geldahl's method is given, if the examiner is kind enough in the sense, the third reaction which I have written now, ammonia plus H2SO4 excess. If the examiner is kind enough, they'll directly give you this. So all you need to do is you can balance this equation, apply the mole-mole analysis. If not given, then you can just take care of the two equation, right? One is when you are titrating it with NaOH in the end, last one. Basically what you are getting is the number of equivalents of H2SO4 which were left out. Okay, and once you have that, you already have the knowledge how much amount of H2SO4 was there in the container which you have taken originally. Is this clear to all of you? We'll look into the question now. So I'll take you to the question so that you can relate to it, right? We were here, right? So I told you that when you have taken this first thing, so you can now relate to the equations, okay? So what we have done is we have taken this organic compound, we have started to heat with concentrated H2SO4, and so that all the nitrogen in it gets converted into ammonium sulfate. Now we have emptied the flask here, contents of this Geldahl's flask here, and what we have done is we have added NaOH to it, so that the ammonia starts liberating. If at all this Geldahl's trap is not there, ammonia will be lost, right? Now the thing is, this is getting trapped here, and you imagine that this is kind of sealed, okay? Otherwise the ammonia can escape from here also. So in this only we have added excess amount of H2SO4, which is kind of, neutralizing the entire ammonia which is released. So in this you are having ammonium sulfate, and you are having basically that H2SO4 extra left out. So you want to you take this beaker and titrate it with the NaOH, okay? That solution you would have made. So here there is no requirement of the formula. Just the basic understanding of the process will do. Now let us try to see this question which is given about this Geldahl's, and you will be able to, kind of understand this. See, the thing is, try to understand the language of the problem. Okay, what they have given you is during the estimation of nitrogen present in an organic compound by Geldahl's method, the ammonia evolved from 0.5 gram. That means they have given you what is the mass of organic compound, which is 0.5 gram. Now the thing is, whatever is the ammonia evolved, it was able to neutralize 10 ml of 1 molar H2SO4. 10 ml of 1 molar H2SO4, it was able to neutralize this entirely, right? Now they're asking you what is the percentage of nitrogen in the compound. Now again I am saying that the examiner is kind enough here, okay, because they have given you directly how much H2SO4 was completely neutralized. They are not giving you how much excess, how much, kind of left out, something like that. So here what you can do is basically you can use this equation. Ammonia is reacting with H2SO4, you will be getting this ammonium sulfate. So if you want to do the mole-mole analysis, then you balance it. So it will be like 2 ammonia. I think now it is balanced, right? 6 plus 2, 8. Now the thing is, how many millimoles from here? Millimoles of F. See, the molarity is number of moles upon volume in ml. Na? So molarity into volume in ml, basically it will give you the millimoles. So how many millimoles I am having? 10 millimoles. So I am having 10 millimoles of H2SO4, right? So according to stoichiometry, 2 moles of ammonia reacts with 1 mole of H2SO4. So how many millimoles of ammonia now? There are 20 millimoles. If it is 20 millimoles, which is 20 into 10 raised to minus 3 moles. Did I get the number of moles of nitrogen? I got the number of moles of nitrogen as 20 into 10 raised to minus 3, which is nothing but 2 into 10 raised to power of minus 2. Can I get the mass of nitrogen? Yes, why not? Mass of nitrogen into this molar mass of nitrogen, which is 14. So it is 28 into 10 raised to power of minus 2. Now, for the percentage, what I am supposed to do is divide this mass of nitrogen upon the weight of the compound, which is 0.5. If you wanted to apply the equivalent concept, then also you could have gone for number of equivalents of H2SO4 equal to, directly we could have written number of equivalents of H2SO4 equal to the number of equivalents of ammonia. But the only thing is here you have got millimoles. So you need to find out what is the normality of it. So when it is given in terms of moles, so you can go by moles also. But only thing is you make sure that you are balancing it. Are we getting it? So that is the way you go for any Jaldas question also. I hope this is clear to you. Okay. Now next is for halogen. See, whenever you are reading this quantitative analysis portion, make sure you know the method name also. Like Carius method is applicable for whom, they can ask you, right? So this is for halogen, right? Now in case of Carius method for the estimation of halogen, you just remember one thing, that whatever is the halogen present in the organic compound, it is being treated with AgNO3 and like, you know, the process is there. But whatever is the halogen there, it is getting converted in the form of AgX, right? Like AgCl, AgBr, AgI. So we are getting the weight of that precipitate. Right? So the thing is here you are able to see in Carius method, the estimation 0.15 gram of organic compound gave this much of AgBr. So again here I told you just apply the mole analysis. Right? So 1 mole of AgBr. 1 mole of AgBr, it contains basically 1 mole of bromine. So 1 mole of AgBr means it is 188 gram of AgBr. It corresponds to how many? This one is basically 80 gram of bromine. So what you have been provided with 0.12 gram of AgBr, it will give you how much? That will be 80 into 0.12 upon 188. So you got the mass of bromine. For the percentage, just divided by the molar mass of it, by the mass of the organic compound which is given, because you have to find out the percentage in the organic compound. Is that clear to all of you, right? Now, when it comes to sulfur estimation, so do remember sulfur in the organic compound is getting converted into BaSO4 precipitate. That's the only thing which you have to remember, nothing else, right? So you are having here mass of the organic compound, this much is the mass of barium sulfate, right? So just remember 1 mole of barium sulfate is giving you 1 mole of sulfur, or it corresponds to 1 mole of sulfur, right? So 1 mole of barium sulfate means it is 233 grams of barium sulfate. It corresponds to 32 grams of sulfur. So therefore, how much you are having? 0.4813 gram of barium sulfate will correspond to what? That will be 32 into 0.4813 into upon 233. This is what, this you have got the mass of sulfur. This you divide by the mass of organic compound into 100, that will give you the percentage of sulfur. Is this clear? It's very simple, okay? Understood? So I'm again telling you, you just remember in which form your element is getting converted. Carbon got converted to CO2, hydrogen got converted to H2O, halogen is getting converted into AgX. That X could be chlorine, bromine or iodine. Sulfur got converted into the form of BaSO4. That's the only thing you have to remember, and just apply the mole analysis and it will be like a cakewalk. Okay. Now, let us go further. When it comes to phosphorus, okay. So in case of phosphorus, basically it is like in 2 ways you are able to identify. In qualitative analysis, you might have known by a kind of series of reactant when we are reacting that phosphorus is ultimately getting converted into this ammonium phosphomolybdate, which is a canary yellow color kind of complex which gets formed. So either in its form or else in this Mg2P2O7, magnesium pyrophosphate. So all you need to remember is 1 mole of Mg2P2O7 corresponds to 2 moles of phosphorus. So they might give you some mass of Mg2P2O7 which is there, and you have to estimate the percentage. Is this clear to you? So there is no need to remember any formula, okay? So here also the same funda, okay? So don't get confused. Either they can give you like in form of Mg2P2O7. So they may give you that during certain experiment, let us say mass of the organic compound is 0.5 gram and certain suppose 0.2 gram of this is formed, right? So you have to estimate the phosphorus there. So all you need to do is 1 mole of Mg2P2O7, it corresponds to 2 mole of phosphorus, right? So 1 mole of this means it corresponds to 222 gram of this Mg2P2O7. So that corresponds to basically 62 gram of phosphorus. Now what you are having here now is basically you are having, let us say they might be mentioning that 0.2 gram will correspond to how many grams? So that will give you the mass of phosphorus. So mass of phosphorus upon the mass of the organic compound into 100, you got your answer. And for oxygen, 100 minus all those things. Percentage of any other element which is present, you'll get the percentage of oxygen. Is this clear to all of you? Right? So hopefully this area is okay. So you just, kind of keep a track of it. One question which I would like to, kind of discuss here from the exercise also, which is again based on the gel dals. One type of method we have already seen. As such in regular classes, I might have discussed it. Now see here what is given to you, this particular question. A sample of 0.5 gram of an organic compound was treated according to gel dals method. The ammonia evolved was absorbed in this 50 ml of 0.5 molar H2SO4. The residual acid, that means the left out acid, it required 60 ml of 0.5 molar NaOH for neutralization, right? Now the thing is, all we know is that the mass of organic compound is given to you. How much is that? Basically it is 0.5. Now they have given you the millimoles of NaOH which was required for neutralization of the excess H2SO4 left out. So can I write the number of equivalents of H2SO4 left out? That will be equal to number of equivalents of NaOH. Remember, number of equivalent is always number of moles into N factor, right? And for NaOH, N factor is 1 only. So basically what I'm getting is, this is 60 into 0.5, which is 30 millimoles only, in fact, you have got. In fact, this is milli equivalents. So if at all I have to write down the equivalents, basically it will be 10 raised to minus 3. Are we getting it? So basically it is 3 into 10 raised to power of minus 3 equivalents we have got of the H2SO4 which is left out. Now, what about it was absorbed in this? So number of equivalents of H2SO4 excess. Do we know that? So basically it is millimoles which is given to you, which is 50 into 0.5, right? Into what you are going to do is you are going to multiply it by 2. Reason being N factor for H2SO4 is 2. I am converting this into number of equivalents. Okay. Now, and this is millimoles. So I am writing like I want to convert it into like equivalents. Are we getting it? What I am doing here? This is what you have done is millimoles. Multiplied by 10 raised to minus 3. That means you have got it converted into moles. Multiplying by 2 means you are converting it into the N factor. So what I'll be getting is basically, I'll be getting this as 5 into 10 raised to minus 2, right? So basically here I'm having this as number of equivalents of H2SO4 left out, number of equivalents of H2SO4 excess I am knowing. So what about the number of equivalents of H2SO4 that reacted? And that will be basically 5 into 10 raised to minus 2 minus of 3 into 10 raised to minus 2. You will be getting 2 into 10 raised to power of minus 2. So did you get how much amount of ammonia or its number of equivalents of ammonia reacted? From that, did you get the number of moles of ammonia? And can I say this is only the number of moles of nitrogen, which is ultimately 2 into 10 raised to minus 2? I got the number of moles of nitrogen. All I need to do is find out the mass of nitrogen, and that will be number of moles of nitrogen into 14. And here also you'll be getting the same answer of what is there in the solved example. I hope these are the only 2 sets of problems which you are having, nothing else. Okay. You could have done the mole-mole analysis also, but for mole-mole analysis, you just have to write down the entire balanced reaction, nothing else. Okay. There is no difference. So this is done. Now let us go further now. So we'll move on towards the alcohol phenol ether revision here. So again, when it comes to alcohol phenol ether, here they have stressed upon basically, kind of identifying primary, secondary, tertiary, benzylic, allylic, Because the thing is, you must, you should be able to identify allylic, benzylic, all those things. Hai? Make sure that you are remembering them. What is allylic? You should be having something like sp2 carbon, and to that sp3 carbon is attached. Hai? This is sp3 carbon, and suppose OH is attached to this sp3 hybridized carbon. So that will be allylic. Hai? So the thing is, you must be able to identify that. So suppose this is there. It is basically benzylic. So you must remember from toluene, if at all you consider CH3, and if you remove one of the hydrogens there, you are getting basically the benzyl, right? Then if at all you remove two of the hydrogen valencies, you will be getting something like this CH. If at all you remove all three of them, you will be getting like this. You'll be calling this as benzo. So benzyl, benzyl, and benzo. Okay, remember that? So based on that only you do. Okay, so this is basically what you tell me about the sixth one. Whether it is allylic alcohol, benzylic, or what it is. Sixth one, whether it is allylic, benzylic, what kind of it is? It is allylic. Very good. And in allylic also it is 3 degree. Okay, so this kind of question is very common. They can ask you, what about this? Is it simply a 2 degree alcohol, or else I can attach any kind of prefix here, allylic, benzylic? Can I add anything here? It is just secondary. Okay. Now, what about this? It is allylic and primary. Okay, very good. Okay. Now let us go further here. Now, when you are revising, make sure that you are not ignoring the naming table here, and especially some common name like glycerol, ethylene glycol, because the examiner can give you like what is the IUPAC name of ethylene glycol. So you must know how the ethylene glycol looks like. Unless and until you are not able to write down the formula of it, how would you write down the IUPAC name of it? Okay, so make sure you are remembering that. Okay, now. Next is basically, one more confusion which people have is with the phenol, aliphatic alcohol, and aromatic alcohol. Okay. So suppose if I give you like this OH, I give you something like this OH CH3. I write something like CH2 OH suppose. And if at all I'm writing CH3 OH, right? Now, first of all, if at all OH is directly connected to the benzene ring, it is phenol. Phenol or derivative of phenol, they are into the category of phenol only, right? Now, this I am calling it as an aromatic alcohol. Why aromatic? See, first of all, why I am calling it as alcohol? Because you are having OH group. Aromatic because you are having a ring here, benzene ring, which is aromatic, right? And this is aliphatic alcohol, CH3OH, ethanol, propanol, all those things, okay? So make sure that you are, kind of remembering this fundamental which is there, okay? Now, let us move further. So here then they have just asked you to write down the name. So names are very simple to write. So you can easily, like I'll ask you a few of the names here, suppose. So what are you going to name this? Definitely, if at all this is not there, it is phenol. Okay, so you have to give number 1 to this, 2, 3, 4, 5, 6. So it should be 2,6-dimethylphenol, right? Okay. And then for this, it is 1, 2, 3, 4, 5, 4-chloro, 2,3-dimethyl, and pentane 1-ol. Okay, clear about this? What about this? Both of them, they are substituent only. OC2H5 and this is NO2. So this is ethoxy and this is nitro. So whenever there are only 2 substituents, so you can always go by giving lower number to the one which is having like earlier in the alphabetic order, if there are only 2 substituents. Okay, so in this case you are having 1 and 2, so you'll be writing 2 nitro or else 1 ethoxy 2 nitro cyclohexane. Okay, I hope this is clear to you. So similarly you can name the rest of the things also. Now next, coming on to the equation here or the question which is given here. Okay, here what they've asked you is you have to find out what are the suitable, you have to prepare this alcohol first of all, and using a suitable Grignard reagent on methanol. On methanol means they have given you that this is basically your carbonyl compound. Do remember that if at all you have to make a primary alcohol, always you have to take which carbonyl compound? HCHO. That is your methanol. If at all you want to make any secondary alcohol, for that you need to take any aldehyde other than HCHO, which is first member, right? And if at all you want to make a 3-degree alcohol, then you need to start off with a ketone and the Grignard reagent. Okay. Now the thing is, whenever we write something like this, HC double bond OH, and suppose RMGX I'm writing in general. Okay. So what do we mean here is basically from the Grignard reagent, you will be getting this carbonyl-like species, R minus, which will be attacking at this delta plus center. And what you are going to get is HCO minus H and R here. If you want to write down MGX, no problem, you can write there. Now the thing is, after that, in the next step, you may supply water or else, H plus, which will be taking up a source of H plus basically. So you'll be having something like this H, R, OH. So are you able to realize we are getting RCH2OH? Now all you need to understand is this CH2 portion which is there, it is coming from the methanol only, right? Now that CH2, basically this portion CH2O minus, are you able to understand? CH2O minus, that belongs to methanol. So now if at all I need to identify what is basically the suitable Grignard reagent here, the thing is this portion CH2OH, it is the input from methanol. Okay. Now the thing is, you just break the bond from here. Okay. And what you are going to make is the Grignard reagent, which is CH3, MgX, you can write. Are you able to understand this, right? Now the similar way here also, CH2OH, it is part of that methanol, because the thing is the examiner has specified it. So this is the part of methanol. So basically what you're going to do is just attach to this MgX. Right? Clear about this? Okay. Now the next one is, you are provided with here, write the structure of the products, okay? So in this products, the thing is this is hydration, acid catalyzed hydration. So acid catalyzed hydration means addition of water. You are having H plus and OH minus, and it also follows Markovnikov rules of addition only. So here, first of all, the electrophile will be added in such a way so that it results in more stable carbocation. And my electrophile here is H plus. So basically it is something like this, H plus and OH minus. Your electron density is getting this H plus first. After that, you are having this OH minus, which can attack here. CH3, CH, OH or CH3. And if you consider water is as such a weak electrophile, so if you don't want like that, so basically you can have something like CH3, CH plus, CH3, water being a nucleophile, it can attack here. And you'll be getting CH3, CH, OH, H plus and CH3. Now again, water can be there, which can easily take up this H plus, right? And you'll be having the alcohol. Okay, clear about that? Now the thing is, this sodium borohydride. Sodium borohydride is a very selective reducing agent. When it comes to lithium aluminum hydride, it is like kind of, it will be able to almost reduce any functional groups, except for alkene, alkyne, and benzene. Now in this case, it is going to, kind of reduce your aldehyde, it is going to reduce your ketone, and among acid derivative, it is going to go for acid halide. Right? It is not going to do anything to the ester. Okay. So the thing is, here it will be intact. Only thing is, this will be reduced back to the alcohol. And always remember one thing here, that 1 degree alcohol on oxidation give you aldehyde, and aldehyde on oxidation gives you acid. So one step, if reduction is possible, it will take to this and again reduction like this. Similarly, 2 degree alcohol on oxidation should give you a ketone, right? And ketones are difficult to oxidize. That's the reason we are not writing further, right? So the thing is, remember, sodium borohydride is able to reduce aldehyde and ketone. Along with that, the most reactive acid derivative, which is basically your acid halide. And in fact, this alkyl halide also it does. And it supplies basically H minus from here. So basically what you are going to write the product as, you're going to write this as OH, and you're going to write this as CH2, C double bond O, OCH3. Getting it? So again, what will happen here? CH3, CH2, CH, CH3 and CH2OH. Clear about this, everybody? Right? And this phenol preparation from cumin is important. Okay, so you must remember that also. Okay, this particular question which I'm talking about. Now give the structure and IUPAC name of the product expected from the following reaction. Catalytic reduction means they're talking about H2 palladium, right? Or else H2 nickel. So you're having CH3, CH2, CH2, C double bond OH. So when you are doing the reduction using it, so one step reduction. So aldehyde, it will come to the alcohol, right? Now the thing is hydration of propene in the presence of dilute H2SO4. So hydration of propene, just now we have seen the CH3, CH double bond CH2, hydration in presence of dilute H2SO4. Or else on the arrow, they can just write down dilute H2SO4, okay? Right, now the thing is it will become CH3, CHOH, CH3, okay? Now, next is reaction of propanone. Propanone is CH3, C double bond O CH3 with a methyl magnesium bromide. That means CH3 MgBr followed by hydrolysis. Like first step is this and then followed by hydrolysis. So what you are going to do is first of all attack this here and you will be getting CH3, C, O minus, here also CH3, CH3. Now the thing is next step is hydrolysis. That means you are providing water here. So basically you will be getting CH3, COH, CH3 and CH3. Getting it? So you'll be getting a 3-degree alcohol. Clear about this? Okay. Achha, somebody was asking me about this one thing. As such, I've already done that in the class. With lithium aluminum hydride. Lithium aluminum hydride will be even able to reduce your ester. Okay. So this is your ester now. So basically you break this first. That means you do the hydrolysis, you try to find out from which particular acid and alcohol it is made. So will you be getting something like this? Double bond O, you're having CH2, C double bond O OH, and you are having CH3OH. This is already the reduced form. It will not be further reduced. Okay. Now lithium aluminum hydride will reduce this acid back to the primary alcohol. This though it can already reduce. Hai na? So with this you will be getting secondary one and you will be getting a primary one. I hope this is clear. Whoever has asked me this question. Okay. Only thing is both lithium aluminum hydride and sodium borohydride, they will not be able to reduce your double bonds. Hai na? Unless and until it is a kind of synonymal system, which is, you know, kind of beyond the scope now. So at present, you need not worry about it. Okay. Now here, when it comes to whenever you are reading NCERT, make sure that you are reading all those things. You need not mug it up, but you need to understand what is the kind of, you know, the trend which goes on. So if at all you are having ethanol, methoxymethane, propane, all of them, first of all, you are not randomly comparing them. Basically, all of them, they are having the similar molecular masses, right? Or else closer molecular masses, then only, or else comparable molecular masses, right? So then only you are comparing it. Okay. Now, when it comes to this, here you are having basically hydrogen bonding existing between its molecule in that particular container. Ether, you just have the dipole interaction. Dipole means like this delta minus delta plus. Here, there is nothing like dipole or hydrogen bonding. So hydrogen bonding is much stronger, you know, kind of the force of attraction which exists between the molecules. So because of that, you are able to see its boiling point higher, then its boiling point is lesser, and it is only because of the weak van der Waals forces that is less. Okay. Now, here again, they have given you, arrange the following sets in the increasing order of their boiling point, and majority of the time it will be the question related to the boiling point, and need not worry about the melting point at all, because there is lots of, you know, kind of discrepancy as far as melting point is concerned. There are lots of irregularities. Okay, so the examiner cannot test you on that. Okay, now when it comes to this particular thing, pentane 1-ol, butane 1-ol, butane 2-ol, ethanol, propanol, and all of them, they are alcohols only. Now, as you increase the number of carbon atoms, molecular mass increases, boiling point should increase, right? Now, the best one should be pentane 1-ol. Let us say this is 1, this is 2, 3, 4. This is 3, this is 4, this is 5. I'm just randomly, you know, kind of writing it. So the least boiling point will be of 6th and the maximum will be of 1st. After that, you are having butane 1-ol and butane 2-ol, right? So butane 1-ol without any branching. So more boiling point. Butane 2-ol branching is there. So basically you are going to have 2 here and then 3. After that, you are having propane 1-ol and ethanol. Which one will be having more carbon atom? Propanol. So basically it will be like 5 first and then it will be like, you'll be having 4. Okay. Now similarly, you have been provided with this pentane 1-ol, N-butane, pentanol, ethoxyethane, right? So now in this case, basically, first of all, maximum will be of this pentane 1-ol, 2, 3, 4, if at all I'm numbering. So basically, you are having pentane 1-ol maximum. Then after that, it is carbonyl compound, which is having the dipole interactions, okay? Now you are having last is 2, and then you'll be having 4. Clear about this? Okay. Now chemical reactions, so already you need to study all of them, okay? Acidity of alcohol. See, whenever you compare the acidity, always remember, you just have to remove the H plus. You remove the H plus from here. What you are going to get is RCH2O minus. This is RCHO minus R. You are going to get RCRR and O minus. Now the conjugate base which you have made, you just have to check for its like stability. So here it will be like, it will be getting destabilized because of the plus sign which is shown by them, right? So least stable, so least acidic, right? Okay. Similarly, do remember that alcohols are weaker acids than water, because when it comes to water, so basically you will be having this na H2O, which will be getting converted to H plus plus OH minus. With alcohol, you are having ROH, so you'll be getting RO minus plus H plus. So out of these two species, which is more stable? OH minus, no, because RO minus, R is there applying its plus I effect and destabilizing the conjugate base. Okay. Now, acidity of phenols. As compared to alcohol, your phenols are more acidic. Okay. Now the thing is, only one example, one particular example which you must, kind of remember very nicely is this particular compound, OH, NO2 and phenol, right? Whenever this kind of question comes, now you need to see what is the kind of effect. You are comparing the acidity here. So this is 1, 2, 3, 4, right? Now you need to see what is the kind of effect these groups are applying when they are present at a particular place, right? So here it is minus M over minus I. I already told you yesterday that mesomeric effect is more dominant over the inductive effect. Similarly here also, only minus I, because mesomeric effect and hyperconjugation effect, they only operate through the ortho and para positions, never through the meta positions. Okay. Now here it is minus M over minus I, right? Now the thing is here, no kind of stabilizing effect. So basically it will be fourth will be least. After this fourth, it is like second, because it like if you remove H plus, O minus is getting stabilized only by the minus I effect. After comparing these two, you will see that 3 is slightly more than the first, because here it is like intramolecular hydrogen bonding in which it is getting engaged. So it is slightly less, not much less. So do remember that. Otherwise, on the basis of minus I effect, we might feel like that NO2, which is at the ortho position, it is much closer. Distance dependent, no? So it is much closer. That means it will be stabilizing more, but that's not the case. Okay. Now let us go further here. So the table which is given to you here is basically you don't have to remember the data. You just have to do the comparative study. Like this 4 we have done, then ortho meta para cresol you can compare. Okay. So ortho meta para cresol, OH, CH3, OH, CH3, OH, CH3, right? Now all you need to see is basically all of them, they are going to be destabilizing in nature now. Here it is hyperconjugation over plus I, here only plus I effect, and here hyperconjugation over plus I. So if I just number this 1, 2, 3. So the thing is, all of them, they are destabilizing the anion which is getting formed, or else the conjugate base which is formed. All we need to observe is which is like least destabilizing. So in this case, the least destabilizing is 2. Because inductive effect is like least effect there. Now out of these two, 1 and 3, here hyperconjugation is distance independent. What is deciding here is inductive effect. So inductive effect group, if it is far away, it will be less destabilizing. So better will be 3 and then 1. 2, 3, 1 should be there. Clear about this? Okay, so you don't have to remember these data. Only thing is just to see the values there. Okay. Now, one question which they've asked you here is arrange the following compounds in the order of their increasing acidic strength. Okay. Now, the thing is they have given you a mixture of phenol and alcohol, and you must remember that the phenols are more acidic as compared to alcohol. Why is it so? Phenols are more acidic because the thing is, if at all you write down the equilibrium of it, it comes out to be O minus plus H plus. And if at all you write down for alcohol, so basically if I want to call this as acid, so it should be able to liberate H plus, no? Right? Now the thing is here it is conjugate base is resonance stabilized. That is the reason we say it is more acidic. So all you need to see is this should be least. Any alcohol, it should be least. After that, you see that all those are phenols. And in that also you check if there is electron withdrawing group or electron releasing group attached to the phenol. If it is electron withdrawing, it will kind of, stabilize the conjugate base and hence it will increase the acidic strength. So if you see carefully, it is 2,4,6-dinitrophenol. And basically what is the other name of this? What is the other name of 2,4,6-trinitrophenol? Picric acid. Wonderful. Okay. So you are having this 2,4,6-trinitrophenol. Okay. It is like this. 2,4,6-trinitrophenol. Then after that you check for, there are like 3,5-dinitrophenol. So it will be like again at ortho and para positions. So basically it is going to help it out. Okay. 3,5-dinitro. 3,5-dinitro like this at meta position. So at least it will be able to apply the minus sign. 4-methyl-phenol and 3-nitro. Now the thing is you are having nitro and you are having methyl. Methyl will be kind of, hyperconjugation. It will be applying the hyperconjugation effect or else inductive effect, which will destabilize it. So among phenol, this should be least. And 3-nitrophenol should come after 3,5-dinitro. And hence the order you are able to see. Now you must remember this particular thing. This is important. Aspirin formula. So always remember, this is like esterification. For esterification, you can have the alcohol and you can have basically the acid or acid derivative. Okay. And in acid derivative also, you are having ester and acid halide only. Okay. And in case of esterification, it is the H which is coming from the alcohol and OH which is going from here. Okay. So the reason for stressing this is, suppose if I write ROH 18 plus I am having something like RC double bond OH. And if at all I ask you like H plus is there, concentrated H plus or H2SO4. So what should be the product? From here it is OH which is going from here H. So you remove water from here and you will be getting like this. This is coming from the mechanism part. Okay. So this one also you must remember, salicylic acid. So you are doing the esterification of it. So basically esterification, for that you need alcohol and acid anhydride. So you can remove the CH3COH group from there. Okay. So all these things you must be able to understand for dehydration of alcohol. Dehydration of alcohol means it is which mechanism? It is even mechanism. So for even it is again similar to whatever is the rate for your SN1. It is 3 degree, 2 degree, 1 degree. So same thing you have to go for it. Okay. Then oxidation, mild oxidizing agent, you must remember, which is PCC, CrO3 in, anhydrous medium. If at all I am writing CrO3 and dilute H2SO4, it becomes your Jones reagent, which is a strong oxidizing agent. So it will send your primary alcohol directly to the acid. Okay. So phenol reactions are also very important. Do remember all these reactions. Okay. And one more question, which is like kind of straightforward, which could be asked is, which one is more steam volatile? Orthonitrophenol or paranitrophenol? Which one is steam volatile? Ortho. Okay. Now halogenation, if it is like bromine and CS2, non-polar, in that case only orthopara. If it is like bromine water, you will be able to see here. Now here the question is, write the structure of major product. If at all you are having 3-methylphenol, right? You are having 3-methylphenol. So basically when you are doing the nitration, so OH based upon this is more activating na plus M group. So it will send at the orthopara position. So para will be major. Now dinitration of 3-methylphenol. Okay. For dinitration, The thing is, they have given you all both the ortho-para position. Okay, if at all you have to do the dinitration of 3-methylphenol, again, ortho-para positions it will be sending. Okay, now the mononitration of phenyl methanoate. This is phenyl methanoate. Okay, now again, this is plus M group. So it will be sending it to the para position. Okay, so do remember that. And this coal-based reaction, which is like, kind of formation of salicylic acid, this is again very important. Similarly, Riemann-Timon reaction also. All these reactions are important. Okay. Now, if at all we are doing the acid catalyzed dehydration of suppose methyl, 1-methyl and cyclohexanol. So what you are going to make? Acid catalyzed dehydration, that means you are going for even elimination. So in that case, what you are going to do is first the protonation, and then you will be getting something like this. And basically, then I can remove. I should be making this more substituted. The thing is, I could have removed from here also, from this place also hydrogen, beta hydrogens. But here, from here, if at all I remove, I'll be getting more stable one. Butane 1-ol. This is butane 1-ol. So first of all, you remove, like by doing the protonation, you'll be removing it. Then you kind of, shift it so that you get more stable carbocation. And after that, there are two possibilities, beta 1 and beta 2. Remove it from beta 1. So you'll be getting CH3, CH double bond CH, CH3 like that. Clear about this? So they've asked you to write down Riemann-Timon reaction, coal-based reaction. Okay. Now they've asked you what is the product which you are going to expect when each of them they are reacting with HCl, ZnCl2. That is Lucas reagent. So this is like simply you are having this OH, and if at all you write HCl, ZnCl2, only thing is you just replace OH by the Cl. Okay. HBr, the same thing. With HBr, just remove OH, put Br over there. SOCl2, you remove OH, put Cl. Similarly, here also 2-methylbutane 2-ol, wherever is OH, replace it by Cl. If at all you are making it react with Lucas reagent, with HBr, replace that OH with Br, and SOCl2, for SOCl2, replace your OH with Cl. Okay, I hope this is clear to all of you. Now, all those things you must remember here. Okay. Now here, the most important, kind of the area from where they can ask you a question is from ether. That is Williamson's ether synthesis. And that is, again, you remember it is SN2 reaction. Okay. So in case of SN2 reaction, see, the thing is, in Williamson's ether synthesis, you require alkoxide. And what else you require is basically alkyl halide. And it should be like primary or secondary. Then only, this kind of thing could be formed, or else ether could be formed. Otherwise, if at all you are having tertiary or something, it will not be formed. So basically here you will not be able to see this kind of formation. But still, if you want to form this, so basically with the bulkier group, you make the alkoxide, and the smaller group, you make the alkyl halide, C2H5X. Okay, this is what is there. So I hope it is clear to you now. So ether they have talked about. So in ether, you just need to remember a few things. Like this question we'll do, and then we'll wind up this ether also. Now the thing is, when it comes to ether, reaction of ether with HI. So that is what is basically. So when it comes to ether here, so basically you just do the protonation. Okay, first of all, HI is given, so protonation, acid-base reaction is faster. You do the protonation. After that, what you're having is I minus, right? Now the thing is, you need to check what is the degree of carbon which is attached like beside this oxygen. This is primary, this is also primary, right? But this primary, then you go for its beta position, it is bulkier group. So I minus, it will attack here, and you will be writing CH3, CH2I. This is a kind of SN2 mechanism which has gone. Now, again, you do the protonation here. Now check for, here it is 3 degree or any resonance stabilized carbocation. So in that case, it will be going by SN1 mechanism. It will be C plus CH3, CH2, CH3 and CH3. And then you kind of attack this I minus over here. Okay. Now, similarly here, HN plus. Now the thing is, you never break this sp2 carbon and oxygen bond. So what you're going to do is, first of all, it will be something like this. Oxygen takes away. You'll be having something like CH2 plus and phenol getting formed. And then I minus, which is there, it can easily attack here. So I hope it is clear to you, right? Okay. So here they have just, kind of appropriate, they've asked you which of the following is appropriate set of reactant for the preparation of 1-methoxy-4-nitrobenzene and why. You want to make this 1-methoxy-4-nitrobenzene. You want to make this one. This is the set of the reactant which is given to you. 1-methoxy-4-nitro. Right? Now the thing is, which one is more suitable? Second one, hai na? So you will be having O minus like this, hai na? Because it is not possible to have. If you are considering this, then in that case you have to break this bond, and it is difficult to break this sp2 carbon and halide bond. Okay. So with this, your alcohol phenol ether is done. Hai na? So now we are just going to focus on only the kind of the salt examples which are there, because as such already in detail we have seen everything. So this is just a kind of a revision session. And I'm again just telling you which portions you have to kind of focus more. This naming also you must remember, okay? Benzophenone, acetophenone, that can be easily asked to you. All these preparation names, everything you must be able to know. Because they are important. Now what is asked to you is, you have to convert hexane 1-ol to hexanol. That means you have to do only one step oxidation. That could be done by any like mild oxidizing agent like PCC, which is there. Hai na? Pyridinium chlorochromate. They have just kind of written it in the expanded form with the formula. Cyclohexanol to cyclohexanone. 2-degree alcohol to ketone. Again, PCC could do, or else anhydrous CrO3 can do, right? Or else copper with heating can also do. Now, parafluorotoluene to parafluorobenzaldehyde. So basically what you can have is the CrO3, mild oxidizing agent, it will be able to do that. Or else you are having this parafluorotoluene, CH3, and this is there. Then this is the kind of Itard reaction which we have remember, right? Okay. Now similarly, ethane nitrile to ethanol. Ethane nitrile you are having CH3, CN, and what you need to do is CH3, CHO. So you can go for dibar H, it will be able to do that. Okay, dibar H is again very, very restrictive. Only with the cyanide and ester it is able to do. Okay. Allyl alcohol to propanol. Allyl alcohol is the CH2 double bond, CH, CH2OH. And you have to form propanol. That means CH2 double bond, CH, CHO. So you take PCC, that will also be able to do, because it is not disturbing the double bond. Now butene to ethanol. So butene, it is like CH3, CH double bond, CH, CH3, and you have to make ethanol, which is CH3, CHO. So all you need to do is do the reductive ozonolysis. So you'll be getting CH3, CHO, because you will be breaking this and making like this. Okay. Now, let us move further. Here, as such, we have already seen these questions. Okay. Anhydrous AlCl3, just remove this Cl minus, and what you are going to do is you're going to put C double bond O C2H5. Now here it is dialkyl cadmium and CH3COCl. So you remove Cd plus 2 Cl minus from here, and then you can have C6H5 CH2 and C double bond O Cl like that. Okay, C double bond O CH3. That's what is going to get formed. Okay, that is already given. Vignesh, that is already given in your notes, beta, and you can refer to it. And some revision has to be required from the student side also. We have already done our bit. Everything, all you need to do is just open your notebook and please read it. That much minimum effort you can do. Now, this is Hg plus 2 and H2SO4. So it is hydration. So CH3C, you're having OH here, double bond, CH2, and all you need to do is like this CH3, C double bond O, CH3, right? And again, this one is kind of, your Itard reaction. So basically you can write CHO and NO2. Okay. So with the physical properties, again, they have, kind of given you something here. Okay, now they've asked you to compare the boiling point. Again, boiling point of this alcohol will be maximum. So this is 1, 2, 3 and 4. So it is easy to identify now. With the alcohol, it is maximum. After that, it is for aldehyde, and after that, it is for ethers, and after that, it is for butane. So they may just play with the number of carbon atoms and it will be done. Okay. So similar thing here, they have done here also. This is like 1, 2, 3, 4, if at all I number, they all are of the comparable molecular masses. So here, first one will be boiling point will be, for the second one, it will be maximum, then first, then 3, and then 4th. Now, all these nucleophilic addition reactions are also important. So make sure that you are remembering them. And this particular table is also important. You must know which one is Schiff's base, how the oxime is formed, how the hydrazone will be formed, what is semicarbazone, right? You just need to remove the H2O. That's the only thing. And with the semicarbazide, be very careful that you have to remove. Suppose this is there, na? NH2, NH, C double bond O, NH2. And if at all they give you H, C double bond O, H. So you have to remove H2O, like hydrogen of that particular nitrogen which is farthest away from this carbonyl compound. Okay. So basically then only you will be able to make the semicarbazone of it. People tend to remove from here, which is the closest to this. Any nitrogen, they just, don't take care of it. So then they'll be scoring -1 there. Okay. So better be careful there. So Clemenson's reduction and Wolff-Kishner reduction, you must be very careful about. Okay. Wolff-Kishner, it is NH2, NH2, and you are having KOH. Clemenson's, it is ZnHg and HCl. Fehling solution and this Benedict solution, haloform reaction, all these must be, kind of remembered there. Now, when it comes to aldol reactions, so for aldol, you remember, aldol reaction is given by those aldehyde and ketones which are having alpha H in them. Okay. Alpha H in them, that means you are having the CHO, CH3 is here. Right. Now the thing is, this is sp3 carbon which is attached to the carbonyl group. Right. And it is having H. So that's what is alpha H. So here they might give you some dilute NaOH and heating. Right. So all you need to do is, if you want to form the condensation product, so all you need to do is you are having CH2H. In fact, I'll write here C double bond O H CH3, and you are having alpha H CH2CHO, right? So you remove H2O and you'll be able to form CH3CH double bond CH-CHO. This is what is condensation product. If they ask you to make the aldol product, so this is alpha carbon, this is beta carbon. To the alpha carbon, see the thing is how we have made this condensation product by removing H2O. Now what you do is, to this alpha carbon you give hydrogen, and to this beta carbon you give OH. So if at all I have to make CH3, CHOH, CH2, CHO. Are we getting it? This is the aldol of it. Okay. Similarly, I'll just, kind of brush up one more thing here. Suppose I'm giving you CH3, CH2, CHO. And here I'm writing, suppose dilute barium hydroxide and heating. Now the thing is, if aldol is concerned, you have to bring the alpha H only. So here you are having CH2, CH3, CHO. Just remove this and connect it. Okay. Make sure that you are removing the alpha H, not the terminal most. Okay. That's what is the major confusion area. CH3, CH2, CH double bond C, CH3 and CHO. Clear about this? Okay. Now the thing is, this is self-aldol. Cross-aldol means either like you will be having two different compounds among which you are doing the aldol reaction. Okay. So if at all you are having something like CH3CHO and you are having something like CH3CH2CHO, and on the arrow it is dilute NaOH heating. So all you can do is two products will be of the self-aldol, right? One product of self-aldol from here, one product from here. Self-aldol means you are removing water molecule from that itself. And the another one will be, suppose you are writing one time oxygen from here, CH2, CH3, CHO. So we'll be removing from here. Okay. So one such product will be CH3, CH double bond C, CH3 and CHO. Another would be if it is CH3, CH2. Next time you take oxygen from the one with supplied hydrogen and you take CH2HCHO. Remove H2 from here. You'll be getting CH3, CH2, CH double bond, CH, CHO. So that's what is cross aldol. Okay. Even if one of the, kind of reactant is not having alpha H, another one is having alpha H, so aldol is possible. Okay. Now next comes the Cannizzaro reaction. Do remember, in case of Cannizzaro reaction, what we are having is, it is only for those aldehydes which do not have alpha H. It is only for those. Okay. So in this case, basically what we are going to have is concentrated. The concentration of the base will also be more. So in that case, you are going to oxidize one of it, like one molecule gets oxidized, another gets reduced. So if it is aldehyde, it gets converted to acid. Now the thing is, this is base, so the acid will not exist. It will be like base will take up the H plus. So that's the reason you'll be forming the salt of it. Now the thing is, another one you have to reduce. Reduce it means make it to the alcohol. Are we getting it? So similar way here also. One of it got oxidized to acid, but you cannot have the acid existing there. Make the salt of it because the medium is basic. And you have to make it like one is reduction. So basically we say that the Cannizzaro reaction is basically a disproportionation reaction. The same species is undergoing oxidation and the same species is undergoing reduction. Is this clear? Okay, now looking at these problems, they are very simple. All you need to do is, this is like hydroxylamine and you have to remove water. So you take H2 and you take this one. So just connect them. Double bond NOH. So we made the oxime of this cyclopentanone. Similarly, this is 2,4-dinitrophenyl hydrazine, 2,4-DNP test, which is given by the carbonyl compounds. Okay. Now the thing is, you just remove H2 and O. So basically, you'll be connecting like this. Double bond NH. Like this, it is here. NO2 and NO2. So you have made the 2,4-DNP hydrazone of it. Okay. Now the next thing is, see the examiner, they have, tried to play a trick with you. Now, if at all you are only focusing on removing water, removing hydrogen from the nitrogen, you might overlook that this nitrogen is nearest to it. You have to remove from the farthest according to the mechanism. So the thing is, what you are going to do is, this is CH double bond O. So remove H2O and O. Okay. So you'll be connecting like this. RCH double bond CH, CH double bond N, NH, C double bond O, NH2. Similarly here, this is oxygen, this is H2O, you remove it. So you'll be making something like C double bond, N, CH2, CH3, and it is CH3. So I hope this is clear to you. And make sure that you are reading the uses also. They're also important. Now for carboxylic acid, make sure that you are revising all these, Naming, it is simple only, right? For the naming, this is chain terminating, so always number 1 to this. So 1, 2, 3, 4, 5. So it will be 2-methyl cyclopentane carboxylic acid. Okay, so this one will be 2-methyl cyclopentane carboxylic acid. Similarly, here also 1, 2, 3, 4, 5, 6. 2,4,6 trinitro benzene carboxylic acid or benzoic acid also. Okay. So I hope it is clear. Jones reagent CrO3H plus. Okay. So do remember this reaction also, where you are having, if all you just have the alpha carbon alpha H, you are having KMNO4, alkaline KMNO4, whatever is the length of the chain, it will be converted to the acid. Okay. So all these we have already studied. You need not worry much about it. Only thing is just kind of revise properly. Now they have asked you, how would you convert butane 1-ol to butanoic acid? Any strong oxidizing agent you bring, and you'll be able to do that. Okay. So they have given you all these conversions. So basically they have just tried to kind of understand the flow here. So if at all it is butane 1-ol to butanoic acid, the number of carbon is remaining the same. So either KMNO4H plus could also have done the same job. Now the thing is, they've brought the strong oxidizing agent, which is Jones reagent. Now again, from benzyl alcohol, you have to make phenyl ethanoic acid. Phenyl ethanoic acid means you have to increase 1 carbon there. So for introducing 1 more carbon, CN has to be brought. Okay. Now the thing is, you first, kind of make it converted to benzyl bromide. Maybe PCl5 or something would also have been employed here. And after that, then you do the Cn minus attack here and bromine will be leaving. And after that, you do the hydrolysis. Okay. So I hope this is clear to you. Now, similar reactions, it is like easy to understand. You can easily understand yourself, right? Now here it is like tolerance test. So basically what you are making is you are oxidizing it, right? So tolerance test is a mild oxidizing agent. Okay. Now all these things, acidic strength. So any electron withdrawing group is going to increase the acidic strength of COH, which you are able to see from here. This is applying minus M minus I. This is like plus M. So it is reducing the acidic strength. Maximum for this, and then this. Okay. So esterification also they have made you understand here. Gabriel thalamide reaction also. Now one name reaction which comes to your mind is basically this HVZ reaction. So basically in HVZ what is done is at alpha H you will be able to kind of substitute the halogen. Right. So if at all it is CH3, CH2, COH, and if at all I give you that red phosphorus, bromine and all those things. Now the thing is at alpha carbon, you just remove hydrogen and substitute by bromine. Okay. So I hope this is clear to you. Now let us quickly see the amines portion here. So when it comes to amines also, make sure that you are, kind of revising this particular naming table. Okay. And you're able to identify which one is primary, which one is secondary here. Okay. So with amines, you just need to look for how many number of, carbon containing groups are attached. Okay. So here it will be primary only because this is only one carbon containing group. It is again going to be tertiary because we are having 3 carbon containing. Here it is going to be primary and here it is going to be secondary. Okay. So you should be able to do that. Now the thing is they've asked you to write down the structure of the different isomeric amines corresponding to molecular formula C4H11N. So you first find out the degree of unsaturation, which is C plus 1 minus H plus X minus N upon 2. So you are having basically 5 minus this is 11 plus this is nothing is there minus 1 upon 2. So degree of unsaturation is 0, right? That means there is no pi bond or else a ring. So you have to just make it like this. So you can have like 4 carbon containing. Now you can also with the straight chain, you can have something like this NH2. With the 3 carbon chain, you can have something like this. You can also have something like this here, right? You can always check by the name. Now the thing is all the isomers, so you can also make like this, and you can also have gone for this NCC like this. And basically how many are there? Carbon are 4, so here it is like this. You can have NHC like this also. You could have gone for, or else like this also. And here you could have gone like this. So these are the various possibility. So whenever you are drawing, make sure that you are, kind of going systematically, going for all the carbon atoms. Then you see, is there any possibility in the same carbon atoms, right? And then you can go for, slightly decreasing one by one and seeing all the possibilities so that you don't miss out on anything. Okay. Now all those syntheses are also important. Now directly going to the another portion. So whichever is the name reaction, it is very important. Okay. Now the thing is, you try to understand this only as a kind of, by means of which you can, form this, or else they can give you X giving you Y, Y giving you Z, that kind of framework. So what you are having is you have to convert this in CH3, CH2, Cl, which is basically ethyl chloride, to the amine which is having 1 carbon extra. So 1 carbon extra means try to think about Cn. Okay. So basically you are having Cl. You are having the Cn minus SN2 mechanism, you will get this. Now the thing is, if you reduce it by lithium aluminium hydride, you are going to get CH3, CH2, CH2 and H2, right? Now similarly, what we are having is again the same thing. You are having one carbon extra in the amine. So again, think of Cn, right? Clear about it? So the same thing with which they have done here. Now the Hoffman bromide degradation becomes important. They have given you the amide. The thing is, Hoffman bromide means, first of all, it will be like amide, which will be there, RCONH2, and degradation means you are removing CO from there and the bromine plus NaOH is there, then only it is bromamide. Propane amine has to be formed. CH3, CH2, CH2, NH2. So basically, can you think of CH3, CH2, CH2, C double bond O, NH2, and if at all you are having NaOH, Br2, all you need to do is remove this CO. You'll be getting it, right? Now the amine produced by the Hoffman bromide degradation of benzamide, like this it is there, na? C double bond O NH2. You remove this, you'll be getting the aniline. Okay, I hope this is clear to you. Now again, basic strength is important. So for basic strength, do remember how easily it is able to give the lone pair of electrons. So 2130, this is an aqueous phase, and this is for methyl. And if R there is methyl, so 2 degree, like this CH3 twice NH I'm talking about. Then CH3 NH2, and then it is CH3 thrice N, and then it is ammonia. And if it is ethyl, it is 2310 with the bulkier group. So make sure you are remembering this. And if it is gaseous phase, then only based on the inductive effect you have to answer. But the examiner will stress whether it is gaseous phase or not. If nothing is mentioned, you have to take it as an aqueous phase only. Okay. Now, the thing is, they have given you one particular example here. In the decreasing order, see, first of all, when it comes to aliphatic, which is RNH2, and aromatic, which is this. Now the thing is, its lone pair will be involved in resonance, so it will be less available for donation to any other species. Yes, ammonia is coming in the last only 21 Sg. Now the thing is, here it will be like plus I, and because of that, it will be helpful. Okay. Now the thing is, it will be helping this nitrogen to release its lone pair of electrons. So out of them, first of all, this is going to be least. You are able to see that? Because lone pair will be involved in resonance. Then this is like ethyl. So in case of ethyl, you are having 2310. So 2 degree first you will be writing, then 1 degree, and then the ammonia, right? I hope this is clear to you. So all these are like basic fundamental things which you are supposed to, kind of remember. All those reactions also you remember. Okay. And then this benzene disonium chloride reactions also, and that is a kind of a versatile one. You must remember them because that is a very important reagent. Let us try to understand this particular portion. Now what you are having is, basically you have to convert your 4-nitrotoluene to 2-bromobenzoic acid. So you just try to understand what is happening in each set. You are having CH3NO2. This bromine is there. CH3, it is hyperconjugation and plus I. This is minus M or minus I. It is deactivating, right? So the thing is, according to hyperconjugation or activating one only, the electrophile will be directed. So that is the reason ortho position it is going. Para position is blocked. Now the thing is, SnHCl, it is going to convert this to NH2. After that, what I want, I employed this NaNO2 HCl or else HNO2 so that I can convert this into disonium chloride salt. And after that, I want to get rid of this. So bring the reducing agent like H3PO2 or else ethanol. In that case, that will be gone. And after that, you bring this cold, like alkaline KMNO4, hot alkaline KMNO4. It will convert this directly to the CuH. Okay, so I hope this is clear to all of you. So this is all from my side. And hopefully you people revise it very nicely and always prepare with a very positive set of mind. Just, kind of focus on each and every problem which is given there. Okay. And do not waste your time, and each and every minute is very crucial. Okay. So wish you all the best.